Minutes. Hey, you know Miranda. All right, welcome everyone to the TIPE 2022 Technology Track. I'm Amiee Elliott. I'm the North American host for the Technology Track, and I'm a researcher in 3D printing at Oakridge National Lab. So our first speaker today is Miranda Moschel. Miranda started her career in the world of powder metallurgy, where she worked in both traditional and press and sinter powder metal manufacturing, as well as 3D selective laser melting. From there, she moved to work at Xerox as a metallurgist on the 3D printing team focused on liquid metal jet printing, a novel 3D printing technology. Her work focuses on the development and improvement of the aluminum alloys produced on Xerox's flagship LMX printer. I've seen this printer in person. It is very impressive. So I'm excited to hear Miranda's talk titled The Science Behind Liquid Metal Printing. All right. And we have our wonderful tech ambassador, Abby, who is helping us today. And let's just see. There we go. Here's Miranda. Hi, Miranda. How are you?
Hi, guys. I'm really excited to be here.
Awesome. Well, I'll leave it to you then. Thanks.
Okay, I'll go ahead and share my screen. All right, so thank you, Amiee, for the introduction. As she said, I'm going to be talking about the science behind the liquid metal printing on the LMX platform from Xerox. And this is kind of the agenda I'm going to go through today. First, I'm going to talk a little bit about who I am and why I'm on this stage, and hopefully why you guys should be listening to me. And then I'm going to talk about where liquid metal printing sort of fits in the industry map today, because it is a novel technology. And then I'm going to step through and talk about the printer overview, because some of you guys may have seen this printer, some of you may have not. But this is kind of what it looks like on the right here. And then I'm going to start getting into some specifics behind the mechanism of magnetohydrodynamics, which is a mouthful, but we'll get through it. And then I'm going to talk about what the LMX printer actually does and what we produce. And then I'll be happy to take some questions from there. So just an introduction, as Amiee said, my name is Miranda Moschel. I have a background in material science engineering, and I started my career in traditional press and sinter powder metal manufacturing. So people who are familiar with it, they know it's a sort of mass production method of manufacturing. So the scale is quite different than what we're used to dealing with additive industry. But it did give me some valuable experience dealing with the nuances of powder metal, which carried over into my first introduction to additive manufacturing, which was via selective laser melting. Um, right now, I'm working at Xerox as a metallurgist. Ironically, our printer does not use any powder feedstock. We use a wire feedstock, but hopefully this provides a little background and context for where I'm coming from as I explain these things. So I do want to talk about the industry a little bit. I'm sure you guys have seen graphs like this before, going through all the nomenclature and jargon of different printing technologies. And over here on the right is sort of the metal additive technologies that you guys are familiar with, selective laser melting, e-beam, all the big names you're familiar with. And then, oops, sorry. Over on the left, we have material jetting, which is not typically metal. This graphic specifically says there's only one metal printer that does that. And in reality, the technology I'm going to be discussing is somewhere between these. So we are material jetting, additive manufacturing technology, droplet on demand. So it's kind of a newer branch. So as far as the history of this technology, I just want to frame it a little bit here. It was really only 10 years ago in December of 2012 that the idea of using magnetohydrodynamics for liquid metal drop-on-demand printing was even born. So this is a very early technology. And it was later in December of 2018 that Xerox acquired that technology. So some of you guys might have heard of Vader Systems and a little familiar with that technology. Xerox now owns that technology, and we're really leaning into the expertise that Xerox has for ink jetting. So that sort of meshes with the jetting of liquid metal here. And now here's a video overview of the printer. It's a little marketing focused, so we won't spend that much time on it, but it does provide a good kind of overview of the printer itself. So here is the wire feed. It is kind of off-the-shelf welding wire, so that is an advantage we have here where you have the simplicity of wire without dealing with powder. And this inkjet, or this head, is what I'm going to be talking about primarily, where we have our liquid metal, and the mechanism for ejection really happens here. This is where the magic happens. So as far as print head inputs, that video showed just really the liquid metal, but there are a few other things going on in that print head. Obviously, we have some heater power to maintain that liquid metal. So we are dealing with a pool of liquid metal in the print head that we are then ejecting and solidifies on the build plate. It's a little different than some of the other technologies. So some of you guys who are familiar with aluminum might be saying, wait a minute, that aluminum is going to oxidize very quickly. So in that print head, we do have an argon shielding gas. And what this does is it protects the molten aluminum from that sort of oxidation. That argon sheath also extends to the droplets when we're printing. Now, the heater power puts out a lot of heat, and obviously dealing with molten metal, that gets quite hot. So we also have some water going into the print head. It is a water-cooled print head to make sure that only the parts that want to be hot are hot. Otherwise, you end up with some melted bits. And then the key part here that we're going to be talking about is the pulse that comes from the system computer. This is the pulse that actually ejects the droplets. So we end up with a series of single droplets rather than a continuous bead. So as I said, the mechanism we use is called magnetohydrodynamics. It is a mouthful, and I am a metallurgist, not an electrical engineer, so I will explain it to the best of my abilities. But what we use is a magnetic field coming from a coil surrounding the aluminum, and that then forces the metal through a nozzle where individual droplets form. One misconception that people have when they hear magnetohydrodynamics is that the material we're jetting must be magnetic, but that's not the case. We use electromagnetic induction, so as long as the alloy is conductive, then we can use it with this mechanism. So here is the process breakdown. I'm going to go step by step and hopefully provide a good description. So on the left here, the first step is we're focusing on a single ring of aluminum inside the coil. So the coil is surrounding this already liquid molten aluminum. The coil driver, or the computer I talked about before, then sends a pulse of current around the coil, which, if you guys remember electromagnetics, this causes a magnetic field to form around the coil as pictured in the third step. Those two steps then sort of copy themselves in the aluminum itself, but in reverse. So the magnetic field is then going to cause a current in the aluminum ring itself, but going in the opposite direction. And that electrical current then produces another magnetic field also in the opposite direction. So then you end up with two opposing magnetic fields in the opposite direction. And what this does is it physically squeezes the aluminum and ejects a droplet. So you can think of it kind of as squeezing a tube of toothpaste or some ketchup. So that's how we start pushing the aluminum out. But we also found the key to get droplets on demand instead of a continuous stream is actually you have to turn off the pulse. So when you turn off the pulse, this whole process kind of reverses. And you have to keep in mind that these are on very rapid timescales. So when the process reverses, it actually pulls the aluminum back just a little bit. And this combination of pushing some aluminum out and pulling it back just a little bit is enough for the droplet to break off the meniscus, and we have a nice spherical droplet coming off of that. So that all sounds fine and dandy, but I did want to show that we can actually print parts with this. These are the kind of types of parts we would end up with. I think these are typical of the surface finish we get. And I just took some images of example parts, so pumps, fluid management, brackets, those sort of things. And these are just example parts. However, we do have a partnership with the Naval Postgraduate School, our first customer, and these are some of the parts that they are printing and evaluating. So since it is a first generation technology, you guys are familiar, it's going to take some time to verify the process and the mechanical properties before people are comfortable using it in structural applications. But I thought these were some nice examples. They're looking at how they could use it to help the US Navy. So light fixtures that break frequently, wrenches that go missing, valve handles that endure a lot of abuse. Those are parts you could kind of quickly print and have a replacement for on hand. Now, I wouldn't be any kind of metallurgist if I didn't show you guys at least a little bit of microstructure. So I did kind of want to talk about the quality of what we print. I haven't talked about what alloy we use, but it is an aluminum called 4008. So 4008 is the chemical designation for the welding wire. And on the right, you have A356, which is the casting equivalent of that chemistry. So these are chemically identical, but on the left, we have a microstructure example of what's come off of our printer. And on the right, we have an example of what comes out of castings. And these are both in the as printed or as cast state, so they have not been heat treated. with this 4008 aluminum, the primary strengthening mechanism is from the precipitation of silicon and magnesium. So these darker particles you see interspersed on either the casting or the printed part, those are the silicon particles. So you can see on the printed part, they're very evenly dispersed, whereas in the casting you end up with these sort of globs of the aluminum matrix. So the fact that it is so well dispersed kind of lends itself to some strength in our application. However, I hinted at the fact that these parts are typically used in a heat-treated state. So when we do heat treat it, you can see that our microstructure coarsens itself, and this is very typical. Um, and it's still, very well dispersed, all the silicon particles. You also see that some of the particles have become more rounded, and this also lends itself to some strength. So as far as mechanical properties and physical properties, I would say that the surface finish is sandcast comparable. It's not the smoothest surface finish, and if you have critical mating surfaces, you might still have to machine those surfaces. But I think it is a pretty standard kind of surface. And then our density is greater than 99%. You guys are probably aware there's some nuance in with regard to density measurements, whether you're using Archimedes or CT scanning or image analysis, and they all agree that it's above 99% or 99.5, which I think is great for a technology that's really only been around for, just barely 10 years. And then you'll see some tensile data. So on the left, we have a baseline for A356 sand casting from the ASTM standard. And on the right is what we've achieved in printing. So this is still, first generation technology. We're still developing. But as a metallurgist, I'm pretty happy with these numbers. We're above the baseline. Especially the elongation is pretty good. We do, of course, see some differences between horizontal and vertical orientation, which I think is fairly standard for the additive industry. But of course, we are working to understand what drives those differences and how we might improve our printer to improve upon those differences. So overall, I think this is really a unique technology that's come a long way in a short time. And I'm very excited to see where it goes from here. So I'd be happy to answer any of your questions at this point. But also, if you would rather contact me privately, I just put my email up there for reference. So thank you guys.
Thank you so much, Miranda. That was super fascinating. I'm always interested to see what the latest on the magnetojet technology is. So thank you so much. We do have a lot of questions, so let's get right to it. The first question in the Q&A tab, just a reminder, if you have a question, there's a chat tab, and then there's a participants tab, and then there's a Q&A, so you can put your questions in that Q&A. The first question is, what is the droplet size and the geometric resolution that you can achieve?
Yeah, so our droplet size is around 250 microns. So that's fairly different from the layer sizes that you might deal with in SLM or binder jetting. But what that does enable is very fast printing. So we're laying down a lot of material very quickly.
Excellent. Next question is, what materials other than aluminum have been tested with this system?
So we are still exploring new materials. Like I said, it's kind of a first generation technology, so there's some work that has to happen before we start exploring other alloy families. Since we are maintaining molten metal, the process does sort of naturally suit itself to lower melting point metals, which is why we started with aluminum.
There's a question that I don't understand. It's what are the considerations of X? I don't know if you understand that. If not, we'll just pass it on. And if you want to ask that question again, Feel
I
free
think that
to.
was like an example question of how to use chat.
Oh, good job. You figured it out. I couldn't figure that out. Okay, great. All right, next question is, are there any residual stresses after printing? And how do you support the part on the print bed?
So there are some residual stresses, but since we're printing and cooling on the print bed itself and the print bed is heated, we found that the residual stresses are fairly low, low enough that we typically don't have to concern ourselves with distortion when removing from the print bed. And I think the second part of that is how is it supported on the print bed? Typically, we print directly onto the bed itself, and we can print 45 degrees, I think, without any supports, and our supports are still being developed. So we try to print without supports, of course, if we can, and if we can't, then we're still kind of improving our supports. Oh, Amy, I think you're still muted. Sure.
How much post-printing cleanup are you doing? Are you doing machining?
Yeah, so usually we don't have that much cleanup to do. It's just been kind of the applications that we have been printing don't require it right now. I'm sure if we had, critical mating surfaces or tolerances that were outside of what we could hold with the printer, we would be doing machining or polishing or things of that nature. But right now, our post processing is pretty much limited to the heat treatment. I don't think I've discussed part removal from the build plate yet, but basically what we do is it's printed onto the build plate and then we put that build plate into a cooling tank, and the differential and thermal expansions between the build plate and the part that we printed allows it to just pop off. So it is a very simple part removal process. You don't have to worry about sending the build plate to be machined or resurfaced or anything like that.
Excellent. The next question is, would the sisal droplets not oxidize while you're printing the next layer?
Yeah, that's a very important question. And the answer is that the argon that is circulating in the print head is also kind of used as an argon sheath around the jetting stream. So it's similar to what happens in welding, where welding also uses a sheath cover gas to protect the metal from oxidizing.
Perfect. Do you foresee 6000 series aluminum being material Xerox could provide? And if so, what solidification issues do you expect?
Yes, 6,000 is a popular question, of course. I think everybody wants 6,000 series aluminum, but I can't really talk about what's under development right now.
Right. Lots of questions here, so this is great. What's the minimum wall thickness?
Um, Gosh, the minimum wall thickness, I'm not sure what we publish in the design guide right now, but I'm pretty sure it's about 0.2 millimeters. Um, Whoever asked that question, if they want to email me, I can get in contact and send them the design guide if they would like.
Perfect. And then what's the maximum size of printable parts?
I think our build plate is 12 by 12 right now, although we rarely use that large of a space while printing. Um, and then height-wise, I'm sorry, but I'm not sure. I can also send the design guide to you and say what our current recommendations are.
All right. Yeah, still lots of questions. It's great. So what advantages does liquid metal printing offer over powder bed?
So I think I touched on one of them, but we're very fast compared to powder bed. I started in selective laser melting, and it was kind of shocking to me how fast we were. But we could, print some parts in 20 minutes that I think would have taken hours on an SLM. So it is very fast. We're ejecting those droplets at a rate of 30 or 40, 300 or 400 hertz, excuse me.
Do you expect any challenges in printing taller parts, i.e. achieving precise droplet deposition when the part grows vertically and given that the bed is moving?
Yeah, so I believe we're working right now to enable taller parts. Right now, I think a common problem when people try to print taller parts throughout the AM industry, and one that we're seeing as well, is maintaining part temperature from the build plate to the top of the part, because our build plate does provide heat to the part.
Definitely. Okay, so what advantages does liquid metal printing? Okay, I think we already had that question. How about this one? With the drop size of 250 microns, what is the typical resulting layer height and pixel size? I'm guessing that the pixel size is not uniform.
Yeah, so as the droplets fall, they kind of splatter and spread out a little bit. I would still say that they maintain their circular shape, um, but typically our layers are around 0.24 millimeters, I think, so very close to that 250 micron droplet size.
All right, last couple questions. What material is used for the metal container and nozzle?
Oh, I'm not sure I can talk about that. Um, I would say if you're interested in that, then, containers for handling molten aluminum have been around for a long time, and probably the casting industry has some ideas there.
Awesome. What environmental controls are required for your machine?
So our machine is kind of open air. Really, all we require is a dewar of argon to provide that circulating argon in the print head as well as the sheath. But there is no sort of like vacuuming down process or purging process in a chamber similar to what you would see in SLM. It's only that argon sheath.
Great. And you had already touched on the mechanical properties, how they vary in the horizontal and vertical directions. I don't know if you wanted to bring that slide back up or not. That's totally fine. Let's see. But yes, I think that the answer to that question was yes. And then the next question was, how many materials can be used in the machine?
So right now we only have one material released, which is that 4008 aluminum I was discussing. Um, but I think, keep an eye on the news. We are expecting to release more soon.
A couple questions you may not be able to answer live, but how many customers do you have utilizing the machine today? And then what is the cost of the machine?
Yeah, if you'd like to know the cost of the machine, I would have to put you in touch with sales. But I can say that it's comparable to the cost of other sort of similarly sized metal printers. And then as far as customers, the only customer I can talk about I mentioned, and that was the Naval Postgraduate School. Other than that, all I can say is, again, keep an eye on the news because there are some deals in the works.
All right, we'll call this the last question. Thanks so much
Okay.
for answering all these.
Of course, I'm
Okay,
glad people have questions.
yeah, for sure. Um, Whoops. Okay, so we have two now. um, do you ever run into problems with satellite droplets at the nozzle or splashing on the substrate?
So first, satellite droplets. Yes, if there's a problem with the jetting, then we do kind of see a secondary stream, and that's an indication that something needs to be adjusted on the printer. But typically only happens when something is kind of out of whack with the process. And then splashing on the substrate, I don't think we've seen that. Um, it could be possible. I suppose I've heard of incidents of what we call bouncing droplets. Um, but that's typically on the first layer. And again, it only shows up when something is kind of out of whack with the printer. And if we saw that, we would have to fix something.
Gotcha. All right, let's conclude the Q&A. Thank you all so much for your questions. If we didn't get to your question, feel free to reach out to Miranda directly. And thanks again, Miranda, for this really exciting talk.
Sure. Thank you, guys. I was really happy to participate.
All right, thanks. Bye. All right, we are ready for our second talk of the technology track. Thanks again for joining. Our next speaker is Nanci Hardwick. She's the CEO of MELD, MELD, the Manufacturing Corporation, MELD Manufacturing Corporation, and AeroProbe Corporation. MELD has changed the scale of metal additive manufacturing with its solid-state printing process. Nanci has led MELD from a concept to commercialization with several awards, including R&D 100's Most Disruptive New Technology worldwide and the Edison Award. The company holds over 24 patents and manufactures industrial MELD printers capable of printing aluminum, magnesium, copper, titanium, steel, and more. AeroProbe provides the aerospace industry with air data systems designed to improve safety and performance of unmanned aerial vehicles. AeroProbe also designs, manufactures, and collaborates multi-hole probes used by researchers around the world for design validation. Nanci was the founding member and board chair of the AUVSI Ridge and Valley chapter. She's the board chair for Rona-Blacksburg Technology Council. She's got a lot of different positions. I won't go through them all. But she's an amazing, amazing woman and received so many awards. We are so grateful to have you today. Thank you so much, Nanci, and take it away.
Thank you, Amiee. Can you let me know if you can see my slides?
Yes, ma'am. We are good to go. You look great.
Thank you. All right, fantastic. Okay, well, thank you for the opportunity to be here. I'm really excited to share my company and our technology and this program with so many of you, and I'm just grateful to be part of the conversation. I know that not everyone has become acquainted with the MELD technology yet, so I'll start by saying we are located in Virginia in the United States. This is a newer company. We were founded in 2018 and have come to market with printers and services using the patented MELD technology. What's different about MELD is that it is solid state. The material stays below the melt temperature, and this enables a lot of great attributes for the printing itself and also for the parts that are printed. So before I start with a video showing you, I'll ask you to note a couple things as you watch, and then I'll let you just watch. One of the things about staying below the melt temperature is we're keeping all things at a low temperature. And so when you watch this printing video, you'll notice we're printing on a very thin substrate that is very simply fixtured, and there is no distortion. In fact, when the part came off after printing, it was as flat as you'll see it in this video. So here's your substrate, simple fixturing. And then you'll also notice right away that we're in open air, making this very large part. 10-foot cylinder in aluminum 6061. I heard someone just ask Miranda about that. So we are printing here in the 6000 series, and that's about 3 meters in diameter. So we'll stop here and explain what's happening in the process. We have a nice close-up view at the point of deposition. So this schematic will help us explain it. As you can see in the bottom right, we're moving material through a hollow tool. So really simple concept. This material is under force in the z-axis and also is benefiting from shear forces that are created during the rotation of the tool. This allows us to put enough energy into the material that we're printing for it to plastically deform, and simultaneously to put energy into the material we're printing onto for it to plastically deform just under the point of deposition. This allows these two materials to literally be stirred together. You can see discrete layers here as you stand on the outside of the part, but this outside edge will be machined away. And if we were to look at a cross section of that material after the machining away of this exterior skin, we wouldn't even be able to tell that it had been 3D printed. There would be no evidence of these layers. The microstructure will be uniform through the layers and in every direction of the print. So one of the great things about the MELD process is that we are printing fully dense material. We're done once it's printed, and we're able to print, as you can see, in high volumes. So in terms of the program and the opportunities that MELD offers, and in fact where MELD's place is as a process in the AM market, it all comes down to the fact that it's a no melt. And so just another tool in the toolkit, and really on one end of the spectrum in terms of size and print rate. We make trades all the time, and so we can talk about some of those in a bit. You saw the high print rate. We talked about fully dense, wrought properties, great properties from the printed material, and we talked about its simplicity. The great thing about a simple process is that it lends itself to predictability and repeatability. And we'll talk more about what you can print with, but this technology has so much freedom for the user, so much flexibility. This is a great time to navigate around supply chain challenges with the materials available to us. And we looked at a record-breaking part being built. We feel big is beautiful, and that MELD was made for parts measured in meters, not millimeters. And one thing that I'm personally very excited about is the opportunity with the same machine, with the same process, to conduct repairs. Whether it's cast parts, forged parts, it doesn't matter. You have an opportunity to put a part on a machine in open air and add back material. And with sustainability being top of mind for all of us, this is a great tool for that. So let's talk about how this technology is being used for the world's largest printer, and how big is the world's largest printer, and whose printer is it? This is something that we're so excited to be a part of. There's a team of people working on it, but ultimately it's being led by the U.S. Army. And some of the information I'm about to share is courtesy of the Army. The program is focused on and is designing and manufacturing now a printer with a build space of 20 feet by 30 feet by 12 feet in height. So the equivalent is just over 6 meters by 9 meters by almost 4 meters in height. Really mind-blowing dimensions. So with this printer and with the MELD technology, we will be printing parts at a scale never seen before. And when I say parts, this is what I mean. I mean entire ground vehicles. Very, very excited to share this with you all. The program is referred to as the Jointless Hull program, and really this slide and these graphics explain what that means. The desire is to take advantage of what additive manufacturing has to offer to ultimately save lives, because there are humans inside these vehicles, and to leverage all of the flexibility in design, the new alloys, and in some cases, the speed to deployment that additive can offer. So the program's objectives are very simple: to build a tool that allows printing at this magnitude, to develop the qualification and expertise in parts and alloys using this technology at this scale, to utilize the Center of Excellence for Advanced Manufacturing at Rock Island Arsenal for the printer, the development, and also to leverage a smaller scale printer in which some of the qualification activities can be conducted, and then to print and to utilize this technology. So when we think about, and in fact, what was shared, the considerations for which technology should be leveraged for a printer of this scale, many of the same objectives that probably all of you consider in your manufacturing responsibilities were considered. Size, it needs to be a technology that can print parts of this size. When we're talking about gigantic parts, speed of print matters, and materials is a special consideration here, because this is a tool for generations to come to leverage. So it needs to be able to use today's materials, tomorrow's materials, and the future's materials. And this is something that MELD was uniquely able to offer to the program. Quality and performance are always of utmost importance, as is cost. And cost is something that is about the process itself, about the logistics around the process, about the infrastructure for the process, how much power, for example, it might take, or if it requires atmospheric shielding, but it's also about the raw materials. And one of the great things about the MELD process is that off-the-shelf material can be used. So as I mentioned, these are solid rods that go into the printer, not powder, not wire, not a material whose chemistry was especially developed for additive. The last and unique attribute that was considered for this particular program was the ability to make a jointless hull. And that came from an awareness that joints created by welding created opportunities for weakness and ballistics resistance, and a desire to have a uniform microstructure, a uniform build from the bottom up, and that's something that the MELD process can do. So these are some of the considerations and some of the reasons why this solid state process is really well suited to be the additive tool to go on a large format machine that will also be subtractive to build these jointless vehicle hulls. Some of the other things that were considered and observed about the technology during the competitive process in which it was selected was the demonstrated ability to make complex geometries and also to build larger components with very thick wall thicknesses. And here again, we can see open air printing and that stirring action. We talked previously about the dynamic recrystallization that occurs at the point of deposition. What this allows is grain refinement, and grain refinement has a lot of good properties and outcomes for performance. So I'll give you an example here. We're looking at the before and after of an aluminum 7075. And these EBSD images are both using the same scale. So on the left is an image of the material that would have been used in the printing. And on the right is an image of the material that was printed. And you see some just extreme grain refinement here. In all cases, we see grain refinement in the printing of the MELD parts. And this is always uniform in all directions, and that equiax grain structure is beneficial. Usually smaller grains translate into performance attributes like greater wear resistance, greater corrosion resistance, and often greater strength. And this is a contributor to what we see in materials where we have qualified against forging standards. And this, of course, was of great interest to the Army in the selection of MELD for the printer as well. So aluminums, magnesium, great for lightweighting, titanium, great for lightweighting, but stainless steel, nickel-based superalloys, all printing to a forged standard. And I know it was asked about aluminum 6000 series in the previous presentation, and that is something we can do. That's one of the great things about a non-fusion based process is so many more alloys are available to us to print. And you can see here a 7075, but 2000 series as well. These are fantastic alloys, especially for the aerospace industry who is interested in utilizing them for lightweighting. And lightweighting is something that is relevant not only to aerospace, but to space, to ships, to trains, to ground vehicles. Lots of opportunity around these alloys, and now we can really unlock their potential by combining them with the 3D printing technology. So how we do our testing to confirm isotropic properties is perhaps take a build similar to the one we just saw and harvest many samples from it. Here showing samples from the XYZ, what those look like after they're machined. They go off to a third-party lab or customer lab or our own lab, and tensile testing is done to look at the ultimate tensile strength, yield strength, and elongation. And then these in quantity are compared against the standard. And this is essentially how a qualification program is conducted. There are many more attributes to qualify against, but this is always a great baseline. So very much of interest and something that we'll be seeing done on customer printers and these Amiee printers as well. But as I mentioned, the most important thing that we can offer is the ability to have the user print any material that they would like. And we've certainly demonstrated many at our facility in Virginia. This is an ever-growing list, and at this time, there's no known limit to metals that can be printed with MELD printers. So in terms of future-proofing, this technology has a lot to offer to allow for growth and innovation in other areas. Another consideration for the Army was that MELD already is producing off-the-shelf printers. This is one of our smaller printers, the L3. You can see easy to use user interface, lots of build volume. It's about 14 cubic feet. The next size up that we offer today is about 82 cubic feet, and we're about to launch an even bigger printer this year, so stay tuned for that. Having a lot of knowledge about materials and MELD performance is difficult with a new technology. So I've shown you some of the things that we've done. It has been helpful to have the credibility of such great organizations awarding the technology and the company honors since we got started in 2018. So this has definitely helped us to demonstrate what's possible. Of course, nothing says it like printing things. So these are some of the initial parts that we were able to print for the Army in conjunction with this program. And you're looking at a near net shape of a vehicle component here. This is what we used to think of as a big part, but now we know they'll be even bigger very soon. And just to show how important it is to be able to take ideas from concept to printer, I wanted to show everybody. I'm sure you're familiar, but if you're not, it's nice to see what a slicer can do. So it's important for MELD customers to be able to take their parts from a CAD model, for example, and move it through a program that helps define how it will be built on the machine. So this is the part we just looked at, and we're going to see it being built layer by layer in the slicer software environment. And actually what we're watching is the tool path. So this is 2 tracks overlapping each other per layer on the build. And what that looks like in reality is this. And so this is a great demonstration of how you can build even bigger wall thicknesses with the ability to do overlapping tracks. This is something that we would have tested out at our facility, determined how much overlap is needed, and then done some analysis just like we looked at to verify that that material in that overlap area has the same quality as the material of a single track wall. So these printers are standard off-the-shelf metal rod. We do have printers in our facility that use powder, and we have demonstrated the ability to recycle materials with those. So there's a lot more that the MELD technology has to offer. It's been really great in our facility to be able to run these printers in an open air environment. The solid rod filler material allows us to completely eliminate powders from our facility. So we eliminate a lot of safety equipment that is necessary to manage powders, and we eliminate the hazards. Without atmospheric control around this machine, we are also operating in a very green way, limiting the use of gases, and it's a very low power process. This is basically a CNC machine that puts the chips back on. We build the part in a very machine shop-like environment with machine shop-like tools, and our operators are former CNC machinists, so it's really very easy to use. So as I said, this is what a big part used to look like. This is what a big part is going to look like, and this is what a big printer is going to look like. This printer stands at 42 feet tall. It will come online at the end of this year. I'm very excited to give you a picture of me standing in front of this machine, but pointing out to you, here's what a 6 foot tall human looks like. So just give yourself a moment to put yourself right there and imagine watching that part being printed by this equipment. And if we look at that part that's being printed there, I'll bring it full circle back to where we started, which is here. So this is printing at a scale just never before imagined. I couldn't be more excited about it. The Army believes that this will be a game changer, and so do I. Thank you so much for letting me share it with you.
Thank you, Nanci. That is just mind-blowing. I cannot wait to see this technology. And I'm not that far from Blacksburg, so I want to come see it. So
please come.
You know. Awesome. All right. Well, we have several questions for you. We'll try to get through them as quickly as we can. The first question is, when considering size, especially at that scale, what are the tolerances that can be held, i.e. how much material needs to be machined off to obtain the final desired dimensions?
Yeah, that is a great question, and one every customer asks us. So we have some ability to control our track width. Our minimum track width might be 1/4 inch. Our maximum track width might be 2 inches, so quite large. Oftentimes, a part wall thickness might vary more than the MELD wall thickness. So we find that we are operating really inside some wide tolerances when we nest the finished part in the MELD model. We have usually a margin to spare. That exterior that gets machined away is very small, maybe 1/10 of an inch, but it does depend on the material being printed.
And along those lines, what is the least achievable wall thickness, or I guess the thinnest wall thickness?
Yeah, I don't know what the thinnest is. Like I said, to date, it's been about 1/4 of an inch, but ever since we got started with this technology, there's been a demand to go bigger and not a demand to go smaller. So our efforts have been on scaling up. I don't know how much we can scale down. but I hope to get the chance to find out one day.
The next question is, how do you deal with oxidation?
Yeah, that's the great thing about the melt process is staying below the melt temperature really removes the risk of oxidation. So it's an opportunity to just come at printing from a completely different way.
Let's see. What's the maximum overhead you can do?
Also, don't know the answer to the maximum, but we have done about 45 degrees.
And is there a difference between this process and friction stir welding? I think is the question.
Yeah, great question. A lot of similarities, but there is a big difference. Friction stir welding is not additive and cannot be additive, and MELD is additive and cannot not be additive. So friction stir welding is great for combining existing material, 2 plates, for example, and MELD is great for adding material.
All right, we'll take one more question. This one's a little cheeky. It says, is it really jointless since every single layer is technically joined together by welding?
Yeah, so thank you. I appreciate the opportunity to clarify that every single layer is not joined by welding. It's joined by MELD, and MELD is so different from welding because we're not melting. And really where one of the places where that offers an advantage is at the interface. So there is no interface in between 2 layers. In fact, as I said, if we cut the material apart and have a look at it and evaluate it, we won't be able to see where the layers were at all. So yeah, it's really different, and it takes a little bit of time to wrap your head around what's happening. And so yeah, thank you for the opportunity to share it.
Awesome. Thank you so much. We'll go ahead and step off the stage and get ready for our next speaker. Thanks again, Nanci.
Thank you.
All right, well, I'm excited to introduce the last speaker of this block. This is Amiee Jackson from Oakridge National Lab. So her bio reads, following her bachelor's in mechanical engineering at Rochester Institute of Technology, Amiee joined Oakridge National Laboratory's manufacturing demonstration facility as a technical professional in 2020. She works on additive processes designed for additive manufacturing and systems integration. Her experience encompasses material extrusion, powder bed fusion, and directed energy deposition processes with an emphasis on large scale systems. So we're just going to take a minute to let Amiee get settled, and we will join you right back. Well, thank you so much, Amiee, for presenting today. And yeah, I'll leave the floor to you. Thank you so much.
Thank you. Okay, so thank you all for joining me today. I'm Amiee Jackson, and I'm presenting. I'll be talking about some of the work that a whole slew of folks around my organization have been working on for years, as well as some that I've been working on myself. To make sure that we've got a common framework, I want to quickly describe my organization. I'm at the Manufacturing Demonstration Facility, which is one of the user facilities at Oakridge National Laboratory. We're nestled in the hills and ridges of eastern Tennessee, which, if you've never been, is a gorgeous place to be. Now, ORNL's mission, since its beginnings with the Manhattan Project, has been to rapidly transition fundamental science to manufacturing. We're DOE's largest science lab, and it's honestly incredible, the breadth of expertise that there is across the lab, including in some core areas like neutrons, high-performance computing, and advanced materials and processes. At the MDF, our mission is to reinvigorate United States manufacturing. We collaborate with lots of different folks from industry and academia, focusing mostly on additive manufacturing to move technologies from low to mid technology readiness level. Now, the MDF is an exciting place to work, in part because of the machines, tools, and systems that we've got around. So here's a little overview. We have over a dozen metal powder bed systems, over 7 large-scale metal-directed energy deposition systems, and more than 4 hybrid systems. Later on, we'll chat a little bit more about a few of these. Now, the landscape of our high bay floor is constantly evolving, so much so that I sometimes joke about being a mouse in one of those constantly changing mazes. Also, a quick plug here. We've got a cool virtual tour on our website if you're interested to dig deeper. Prior to the pandemic, we enjoyed giving tours to visitors and folks all the time, and we hope to someday get back to that. For now, the virtual tour is a great alternative. Today, of ASTM's 7 families of additive, we'll be chatting a bit about the work in binder jetting, directed energy deposition, and powder bed fusion here at the MDF. So let's get started with some binder jetting. Here, we're looking at a demonstration which shows the viability of producing fully dense H13 steels tools for hot work like injection molding. This H13 preform was binder jet printed and then sintered to full density with no infiltration, so this is a single alloy, which is fully dense, and then it was demonstrated on an injection molding setup. Conformal cooling channels incorporated in this design would have been very expensive to create via traditional manufacturing methods. The binder jetting work at the MDF includes metals and ceramics and uses both metal infiltration and single alloy sintering for densification. Another facet to this work in binder jetting is in the digital thread toward creating closed loop control. Environmental variables and process parameter variables sometimes lead to short spreading of powder, particularly when working with new powder feedstocks. So what we're seeing here is the optical data of short spreading interpreted through the vision software to detect where the part is in green and where there is short spreading in purple. In the graph, we can see the purple line goes up where there is induced short spreading, and then it goes back down as the machine adjusts the hopper settings to compensate for the error. So we can see that one more time. Okay, so there's a lot of potential for binder jetting in many industries because of its high throughput. We're seeing major takeover of the metal injection molding industry, and as sintering technology evolves, we'll see the replacement of investment casting and then traditional tool making. One of the issues that holds binder jetting back is handling the green part before it goes into the furnace. Some of our work is delving into automating the part retrieval, depowdering, and sintering steps to address these process limitations. Imagine creating an archaeologist robot that needs to excavate, clean, and handle these extremely delicate and fragile parts. Sounds like an exciting challenge to me. Speaking of robot arms doing cool stuff, we've got quite a few of those around, particularly in our directed energy deposition portfolio. Here, we've been collaborating with industry partners to create and finesse robot welding systems that produce metal parts by welding layer by layer. The configurations include laser and arc systems. Some use wire and or powder feedstocks, and there are many different kinematic arrangements that enable certain geometric complexities and capabilities. This slide shows a quick sample, but we'll talk a bit more in detail up next. So it all started with MBAM. This system is an absolute unit. One of the original demonstrations was an excavator boom, which was printed from mild steel and demonstrated at a construction equipment trade show. You can see this part in the video of this print. Oh, yeah, there we go. And it's also in this image on the upper right. It's that silver shiny part just before the shovel. More recently, we also built a large watercraft propeller too. Here, we made a foray toward out-of-plane pathing and deposition. Using a robot arm for deposition opens up quite a few interesting avenues geometrically. For example, changing the angle of the deposition vector relative to the starting plane. Exploring these design and process spaces has comprised a lot of the work done here. We've also explored applications in repairing and reworking tooling and other high-value components. So this system framework has proven to be incredibly versatile and high impact. Now this system has been developed in partnership with GKN, and it's designed for titanium alloys, which are crucial to aerospace applications due to their strength and fatigue properties, but they're also very expensive. The goal here is to reduce the buy-to-fly ratio by printing near-net shapes instead of machining those skeletal structures from large blocks of material. The buy-to-fly ratio refers to the ratio between the amount of billet material purchased and the amount of material in the end part. For some complex geometries, particularly those that have been optimized for lightweighting purposes, this buy-to-fly ratio can be quite high. This ratio can be reduced by printing a billet that is much closer to the end desired part geometry, thereby requiring less machining. This closer geometry is referred to as near net. The booth gets filled with argon while printing to prevent oxidation and porosity development. Our work with this system has led to several cool demonstration pieces, which are enabled by advances in control systems, such as incorporating height control and homing in on optimal processing parameters. Those processing parameters are really key, particularly for different geometries and pathing orientations. An example of the mastery of the processing parameters is the melt pool geometry control work, where secondary geometry was embossed in the printed component that was not part of the toolpath, but rather part of the site-specific parameters. This example is shown in the image on the bottom left, where you can see the Oakridge leaf embossed on the part. One of my favorite systems right now is called Medusa. There are 3 welding heads on this system, with each mounted to a robot arm positioned at 120-degree intervals around a large rotary table. Each robot arm moves independently, and throughout a print, an individual robot considers work balancing and collision avoidance in its individual path planning algorithm. This path planning occurs live throughout the print, allowing adaptation and error compensation at any point in time. To make matters more complex, the build table is rotating during the print as well, which has been a fun challenge from the robotics perspective, that is, in planning motion relative to another moving object. As throughput is the most critical feature of an additive technology, this system allows scaling not just in part size and complexity, but also in instantaneous output, which is a high priority avenue of interest. When this system is actually running in the high bay, it sounds a lot like an angry swarm of wasps. Now here at the MDF, our hybrid portfolio is one of our youngest and fastest growing. There are many different definitions of hybrid, but what hybrid means to us is the combination of additive or deposition and subtractive or machining processes in a single system. Hybrid offers the potential for combining the strengths from additive and subtractive processes while also mitigating the weaknesses of each. That is, with hybrid, repeatability, precision, good surface finish, and high productivity are possible, along with geometrical freedom, material options, and less material waste. We've partnered with Mazak in the development of the first serial number of 2 of their machines, one of which is a behemoth with a build volume over 1 meter in length and 300 millimeters in diameter. You can see that system in the image on the bottom left of the slide here. There's a little person for scale. Our other systems utilize blown powder, which opens the design space to multi-material applications as well. Now this demonstration on the Mazak showed that using the hybrid approach as opposed to additive followed by machining can not only reduce the production time, but also yield better properties in the end because cooling during the machining step can allow for in-situ quenching. As we mentioned the concept of near net earlier, often in additive, machining is required as a post-processing step. Because of this, part designers must consider not just the limitations of the additive processor system, but also tool access and collision avoidance in the machining step. Additionally, aligning and locating an additive part in a separate subtractive machine for post-processing is challenging thanks to the residual stress warping and process anomalies. So hybrid strategies address and simplify both of these challenges. One major challenge that's been identified in hybrid work is toolpath generation and part modeling. Conventional machining workflows typically require a model of the desired geometry and the billet material, and the workflow works unidirectionally in that material is removed quickly at first, followed by refining paths. Typical additive processes require a model of the geometry to print, and depending on the post-processing required, there may be a final part model as well. Hybrid, however, offers the opportunity to add material, then subtract some, then add again, then subtract, so on and so forth ad nauseum. Modeling the part at different stages in this workflow and planning the toolpaths required to achieve an in-part geometry quickly becomes complex. As such, our hybrid team has been working with many different software tools to test out and refine varying slicing and path planning algorithms. Here we see a few different slicing and toolpath generation strategies that our hybrid team has developed. For example, in the middle, the chord slicing technique shifts the slicing plane from the conventional orthogonal strategy to slicing planes that are tangential to the geometry, which maintains the width of each layer. Here we can see a few more toolpath generation strategies that have been developed and tested out in conjunction with our hybrid team. On the left, there's a common welding technique called weaving, which is taking place conformally to a curved surface. On the right, we're looking at a spiralization strategy that allows for varying thickness along the wall of a cylindrical part without any stops or starts. Now, our work with electron beam melting was the first additive research program at Oakridge. One of the main foci of this research is building the digital thread through in situ process monitoring. From materials development to system and process improvements, we've been testing and pushing the limits of what can be done with powder bed fusion. On the right here, we're seeing the near-infrared imaging time-lapse of a test artifact build. This is one example of in situ part modeling for defect detection. Identifying methods for certification so that printed parts can be used in industry is a high priority for our research. To this end, we're gathering and correlating loads of data on each part. Beyond monitoring the printed part, we're also monitoring the machine configuration, the environment, feedstock quality and chemistry, process settings, as well as simulation data to predict the outcome of the print. Then we're rolling all of that information together to make use of it through process property mapping, Born certified qualification, and the like. We've been developing software tools to make managing and understanding correlations in this data more accessible as well. The figure on the bottom left shows one of our software tools for identifying correlations in this data. One of the most significant outcomes of this work has been that we were the first to control grain structure within additive manufacturing. That was enabled by simulation and all the information from the digital thread. This is a micrograph of an electron beam print where the ability to control grain size was used to spell DOE. Now, how does this work? I'm oversimplifying here, but the main drivers for grain development are heat and time, specifically cooling time. So we can determine what happens where by monitoring and controlling thermal gradients within a part. Where grain structure is fundamental to many material properties, such as strengths, conductivities, permeabilities, etc., the ability to design not just on the meso and macro scales, but on the micro scale unleashes all sorts of possibilities for high-impact additive applications. Stick a pin in this idea because we'll circle back here shortly. Up next, we're going to shift gears into one particular application for powder bed, which is electric motors and generators. Now, to set the scene, why motors? Well, motors are kind of a big deal, particularly from an energy consumption perspective. There's ample room for improvement in terms of efficiency, and it really matters. 300 terawatt hours is equivalent to about 35 nuclear power plants, and quad here is short for quadrillion BTU, or 10 to the 15. That's a number that to me as a kid just meant unfathomable. When we're talking quads, we're talking on the scale of world energy supply and demand. Also, motors are everywhere. They're in fans, pumps, compressors, toothbrushes, transportation. They're all over every sector and all around us every day. And the logical converse of a motor, a generator, is critical to our efforts toward electrification and renewable energy sources. So the takeaway is we need to build a system to apply and explore what additive manufacturing has to offer, which would be grain structure control, materials advances, geometric complexity and flexibility. And we need to use that system to improve motor and generator efficiencies and performance within that system. So enter Saturn. Now, a typical powder bed fusion system has a total build volume somewhere around 0.6 meters cubed. But with this current system, we're talking about 0.25 meters cubed. That's about a 4 times or 4x, a 400% increase. The system architecture is based in a cylindrical configuration where the build plate rotates. The powder dosing, recoating, and lasers all move in Z. This is a game changer because in conventional systems, these three processes, dosing, recoating, and lasing, happen serially or one after the other. Here, we're parallelizing that, and we've made two sites for this to happen. One of the major limitations to powder bed fusion in general has been process speed, and this system is working to address exactly that. There are several additional challenges to this system, for example, powder handling and recovery, achieving and maintaining an inert environment during printing, and process and toolpath planning, but we're making exciting headway. Now, the fastest powder bed fusion systems on the market today are multi-laser systems that boast build rates up to 120 to 500 cubic centimeters per hour at 42 to 60 cubic centimeters per hour per laser. However, these systems' build rates are limited by their serial process flow. At this point, the recoating step in the process is a constant that may often be more significant than the lasing step. By parallelizing these process steps in a cylindrical configuration on Saturn, we unlock the potential for much higher build rates that are not limited by the recoating time, but rather by the laser speed. Not only that, but this system architecture allows the flexibility for adding more lasing and recoating stations beyond just two for even more process rate gains. You can see in the figure on the bottom right, the target build rate versus future size for this system and systems similar to this would be that red zone. Now, beyond just adding more lasers, we're also exploring how to best leverage multiple beams for microstructure control, as well as guide future system development, such as selection of number of lasers, their power, spot size, beam distribution, and their arrangement. This further expands our capabilities to design microstructures through spatial control of laser power. So there are many soft magnetic alloys used in motors today. One of the most common families are iron silicon. Of the myriad material properties to consider in these materials, three in particular tell a story here: magnetic permeability, electrical resistivity, and ductility. Considering the graph on the right-hand side, we can see that the resistivity there at the bottom generally increases with increasing percent silicon, while permeability is this one with the big peak here in the middle, just at about 6.5% silicon. For the purpose of a motor, higher permeability and higher resistivity are exactly what we're looking for, so that 6.5% is looking like a great choice. The trouble is that the ductility of our iron silicon alloy decreases as the silicon content increases. It actually drops off quite significantly, around just over 3% silicon. In today's typical manufacturing processes, sheets are rolled out and then laminations are stamped from the sheets. So low ductility presents a big problem here, as you can see in this image on the bottom left. Because of this, typically Fe3Si is used in motor components, which compromises on both the permeability and resistivity in favor of the ductility. One of our angles in this research has been to process and use Fe6Si by leveraging the capabilities that AM offers. Some of our research has shown that controlling process parameters and scan path allows for tailoring these properties, and we've demonstrated the ability to print Fe6Si. We're also working on developing Fe6Si alloys that will improve printability further. In terms of magnetic and electrical performance, grain orientation, grain size, and defect density also matter. As we discussed earlier, AM offers the capability to tune and control these. Additionally, by controlling cooling rates, we may be able to retain some mechanical properties and improve processability of 6.5% silicon alloys. Now, some folks who are familiar with motors know that most rotors are made of a stack of thin sheets, and this is done to prevent or mitigate eddy current losses. Some of the work that's going on around here is looking at other geometries that additive enables to accomplish the same goal, while potentially offering lightweighting benefits or other potential benefits. Here, the electromagnetic performance of a bunch of different cross-section geometries were compared to see what worked best. This Hilbert filling curve outperformed other designs, and they even compared two different FeSi alloys, the 3% and the 6%, which, surprise, surprise, the 6% had lower power losses than the 3%, so that's promising. Okay, sorry. My work has been our first steps toward printing motor rotors from these electrical steels. What I'm showing here was a first pass for feasibility demonstration, not optimization. So we decided to start small with simple motor geometry and print these from Fe3Si as an initial point that we can compare to later, sort of like a worst case scenario. In the middle photo, we can see the printed rotors after they were cut off of the build plate via wire EDM, where the one on the left has been treated with a chemical rust remover, the one in the middle hasn't been treated with anything, and the one on the right has been annealed at 1200 degrees C for 4 hours in argon. We observed significant grain growth and formation in the annealed sample, so in the top photo, the large shimmery sparkles visible are actually individual grains at millimeter scale, which is kind of wild to see. In the video at the bottom center, we can see the results of a CT scan of an annealed rotor, which show where the most porosity occurred in the print. Next, we had a local motor repair and rewinding company swap out these commercial laminations for the printed cores, and we tested them. Now, when I briefly tested the rewound motors, I noticed a few key things. First, the printed cores functioned. This may sound silly, but they're a solid core, but because they're solid core rotors and not a stack of laminations, I wasn't exactly sure how bad the losses due to eddy current generation would be. Like, how much heat would that generate? The answer was nothing too noticeable when running them for just a minute or two. The printed rotors did have more losses to noise and required about 13 times more power than the commercial motor at 12 volts. The annealed core required more power than the as printed. This made sense because the annealing process improves the magnetic permeability while reducing the skin depth. Without laminations thinner than that skin depth, or laminations at all in our case, eddy current generation was aggravated. Our next steps here will be in creating printed Fe6Si laminations to compare to these solid printed rotors. We expect to see pretty significant efficiency gains in this next step. We're also looking to apply the lessons we're learning at this smaller scale to large-scale components printed with the Saturn system. Now, this is one example of a potential application that our work on the Saturn system and with these smaller rotors may enable. Most wind turbine generators today are doubly fed induction generators, which offer advantages such as variable speed operation over a range and decoupled control of active versus reactive power. However, one of the limitations of these generators are that they use brushes and slip rings, which result in reliability issues and maintenance. Brushless doubly fed reluctance machines retain these advantages while eliminating the brushes and slip rings. As reluctance machines, they also eliminate the potential for bar skin effect and the requirement for windings on the rotor itself. So other avenues of future work we're excited about include multi-material powder bed fusion, topology optimization of motor design, as well as site-specific grain orientation optimization for motor performance. With that, I'd like to thank you all for your time today, and I'll open the floor for any questions that may have arisen.
Thank you so much, Amiee. That was such a fun-filled, action-packed presentation. So many different things there. Again, if you guys have questions, feel free to put it in. There's the chat tab, participants, and then Q&A. So we have a few questions. And the first is probably related to I'm losing my words here. The robotic printing. Have you done any off-axis printing?
Yeah, we definitely have. We've actually done pretty extensive off-axis printing. For example, the propeller that I showed would be a really good example of that.
Awesome. All right, this is a binder jet question, so I may take it if you want. It says, I've had a lot of challenges with binder jet on shrinking and distortion. What tools do you use to predict how the build part will turn out, digital twins, etc.? I do know that there are some software tools out there to predict shrinkage and distortion that are more or less coming of age. They're being developed, so I think maybe in the next couple of years we'll see those out and about. Otherwise, there's a lot of work being done on fixturing while you center to ensure that you get critical dimensions met. So, all right. So this is a question about the Saturn system. How would you maintain a reasonable bed temperature with constant lasing?
That's a really good question. I don't know that I'm qualified to answer that, but I would love to get back with you once I've consulted the people who might know.
Yeah, there's a lot of things sometimes that they just work sometimes. And we don't know why, but yeah, I think Amiee and her team probably have answers to that you can talk about offline. So it's a good question. And then we only have one more question unless anyone else wants to pop some into the chat. So this question is, I've heard that a major obstacle to hybrid is the need to treat a part after printing and before milling. So I think that means heat treat, thus interrupting the hybrid workflow. How do you deal with this? And I know that you were presenting on hybrid, just as, you know, demonstrating some work that's done at the MVF. So I think this is a good question. I don't know. What do you think? It's I think we're definitely dealing with this, and I think there's some technology around that probably we can't talk about.
Yeah, I know with one of our systems, at least, there's a move to like incorporate some of that treatment in the same system. So it's like hybrid in 3 ways rather than just 2. But I'm honestly not the subject matter expert on that. So I would love to consult with some of our experts and then also get back to you, Michael. Thank you so much for your question.
Awesome. All right. Well, that is all of our questions, unless someone wants to sneak one in. But otherwise, thank you so much, Amiee, for presenting on the work at Oakridge National Lab. It's always exciting to see those updates. And yeah, thanks again. So that's the end of this block. And please join the main stage to network in between sessions. Otherwise, we will see you back here at 3:10 Eastern with Leanne Friedrich and a couple other speakers and a great panel at the end of the block. So thanks again. We'll see you there.
All right. Can you hear me and see me?
Yep, I can see you and hear you.
Okay, and my presentation is up. Okay.
Yep, it will be. We can swap it out once Amy comes back, but I can see it, and yes.
Great.
Oh, good.
All right, thanks.
All right. Okay, now do you see on the bottom where it says
Yes.
this year? Okay. Yep. Okay, great. Thanks.
All right, welcome back to the technology track. We're so excited to welcome a great lineup of speakers for this block. Our next speaker is Leanne Friedrich. She's a postdoc at the National Institute of Standards and Technology. She uses simulations and in situ imaging experiments to identify strategies to improve print quality and embedded 3D printing of soft materials. She received her BS in Material Science and Engineering from Northwestern University in 2015 and her PhD in Materials from University of California, Santa Barbara in 2020. Her dissertation, titled Tailored Composite Microstructures via Direct Ink Writing and Acoustophoresis, don't know what that word is, explored strategies to improve print quality in a novel 3D printing technique which used sound waves to manipulate the microstructure of polymer matrix composites. Welcome, Leanne. Thank you so much for being here, and I'll leave the stage to you.
Great, thank you. So today what I want to talk about is how we can leverage material science to accelerate embedded 3D bioprinting. So my name is Leanne Friedrich, and I'm a postdoc at NIST. So I want to start with an overview of some of the common polymer 3D printing techniques so we can situate embedded 3D printing in terms of the material space and how it fills out the material space for polymer 3D printing. So there's fused deposition modeling, which is the most common consumer type. There's vat photopolymerization, and then there's direct ink writing, which is starting to emerge more in R&D spaces. So fused deposition modeling, or FDM, is a nice technique for consumers because it is limited to thermoplastics. So the polymer space can be split into thermoplastics, where you can heat them up and cool them down and still maintain the same properties. So things like ABS, PLA, polycarbonate, those are thermoplastics. The other segment of polymers is thermosets. So those have irreversible bonds. You cannot heat those up and cool them down and reform them. So things like epoxies and polyurethanes and silicones. So the way that fused deposition modeling works is you have this polymer filament that has to be a thermoplastic because you're feeding it through a heated nozzle to make it formable, and then you write out the continuous filament onto a substrate and build up your part layer by layer. So because it's limited to thermoplastics, we need other techniques to fill out that material space and make thermosets printable. So one of the ways you can print those is using vat photopolymerization or stereolithography additive manufacturing. So the way this works is you have a vat that is full of a photopolymer resin. So that means that when you shine a light on it of a certain wavelength, that'll cure it and turn it into a solid. So you submerge your stage into that bath and write out your part layer by layer again. So that takes care of photopolymers, things like epoxides and acrylates, which are a subset of thermosets. But we're still missing a lot of the thermoset space, so we need another technique, which is direct ink writing. So the way that direct ink writing works is you have a reservoir that's full of your ink, and you extrude it through a nozzle and write out continuous filaments onto a substrate. And you can use a variety of extrusion methods. You could use pneumatic extrusion, so you have an air pressure that is pushing this fluid out of the nozzle. You could use a piston, you could use a screw. And then there are a variety of curing techniques. So once your part is written out onto the substrate, you can cure it using a variety of techniques. If it's something like alginate, then you could submerge your part into a calcium bath for ionic cross-linking. If you have certain biopolymers, then you could use enzymatic cross-linking to turn that part into a solid. You could, again, use UV radiation. So all these photopolymers are then going to be printable using direct ink writing. And then there's thermal curing. So if you have something like an epoxy, you could write out your part and then heat it up to cure it. So because you have this big range of curing techniques that are available to you, direct ink writing really opens up the material space to include a lot of those thermosets, as well as some other types of materials. You can print ceramic slurries and ceramic matrix composites using this technique because you have that variety of curing techniques. So people have been able to print things like rubber, ceramic matrix composites, polymer matrix composites, and hydrogels using direct ink writing. Now, the limitation with direct ink writing is that you can only print inks that have a certain range of rheological behaviors. So they have to flow in a certain way. So what we're looking at here is a plot of a variety of different materials where we've plotted the shear modulus, the storage modulus, and the loss modulus as a function of the shear stress imposed on that ink. So what this means is if G prime is greater than G double prime, then that material is going to behave like a solid. And if G double prime is greater than G prime, that means that the material is going to behave like a liquid. So if we look at low shear stresses, you can see that G prime is greater than G double prime. So it's going to behave like a solid there. And that's going to reflect the behavior of the material after it's printed onto the substrate. Inside of the nozzle, we're going to be at high shear stresses, and you can see that G double prime is greater than G prime. So this material is going to behave like a liquid. And then in between that solid-like to liquid-like transition, there is a yield stress. So that's the stress at which this material stops behaving like an elastic solid, starts to behave like a liquid. So that yield stress needs to be high enough that the material won't just collapse under its own weight. It won't just flow onto the substrate if you bump the stage or move the stage around. Another way that you can look at the rheology of these materials is using viscosity curves. So we're looking at the viscosity as a function of shear strain rate here. And what you can see is that these are shear thinning materials. So as you increase the shear rate, you decrease the viscosity. So what that means is if you print at high speeds, that'll decrease the viscosity of the ink. And that means you can still get it out of the nozzle without using exceptionally high pressures. At slow speeds, such as when the ink has just come out of the nozzle, it's going to become more viscous and it'll resist flow and be able to hold its form. So among these inks that are plotted here, at the top of the plot where we have these dark lines, those inks are going to be printable because they have a high enough yield stress that they will not just collapse under their own weight. However, at the low end of this plot, and these light blue inks, these are not viscous enough, they're not shear thinning enough, they don't have a high enough yield stress to be printable using direct ink writing. So that's where embedded 3D printing really becomes useful. So the way that this works is you have a print bath that is full of a support fluid. Usually that fluid will have a yield stress and it'll be shear thinning just like those materials that I talked about in the last slide. So things like carbopol hydrogels or laponite hydrogels, those will be good support baths. So you embed your nozzle into that bath and then write out continuous filaments for embedded direct ink writing, or you could print out droplets for embedded droplet printing. So because these materials have a yield stress, they'll behave like a liquid when the nozzle's moving through them, and that'll allow the nozzles to move. But they'll behave like a solid after the nozzle has left, so they'll hold the form of whatever you printed. So this means that we can expand the available material space into low viscosity materials, and we can print thin-walled structures and delicate structures because we don't have to worry as much about the properties of the ink when you have that extra support available to you. So after you're done printing, you can remove these parts from the bath either by scooping them out or using dissolution in a buffer. So what this means is those blue inks, those low viscosity inks, are now going to be printable as long as we use a support bath. So people have been able to print a wide variety of materials using this technique before, and it's been particularly useful for bioprinting. So you might have seen this paper a couple of years ago where they printed a heart, which actually included human heart cells, as well as some extracellular matrix. So you can print these cellularized constructs and actually use the bath to support the growth of that construct by introducing nutrients that'll feed the cells that will allow this construct to, the cells to proliferate. People have also been able to print cell-only inks. So instead of having all these biopolymers available that'll scaffold the ink, they can print just cells, and those cells have been able to grow and develop tissues. And then you can also print functional materials. So things like electrically conductive hydrogels, things that are at a low viscosity, where you've already tailored your ink to a certain functional property like electrical conductivity. You can still print that ink by using a support bath because that support bath takes care of the rheology aspect. So what I want to talk about in this talk is how you choose a support bath for embedded 3D printing. Usually you already have an ink in mind that is going to support your cells or serve some functional purpose. And so how do you choose a bath that is appropriate for that ink? And there are two considerations that you need to take into account. There's rheology and there's surface tension. So in this talk, I'm going to talk about model materials, which are relevant to bioprinting, but have certain rheological properties that are going to tell us about how the rheology is important. So I'm going to talk about how defects can occur in individual filaments in embedded 3D printing. So this is a simulated filament. You can see that blue column is the ink that's inside of the nozzle, and you have a filament that's coming out of the nozzle. If you look at the cross section of that filament, it's not circular like the nozzle is. It actually has a sort of fin shape. So it narrows towards the top and towards a point. So I'm going to express that cross section in terms of the aspect ratio, the height over width. I'm also going to look at the length of these filaments. So if I ask the printer for a 10 millimeter filament, I want a 10 millimeter filament. Oftentimes, if there are defects, these filaments will end up a little shorter than you intended them to be, and that's going to cause a lot of problems in terms of the shape fidelity of the part. So we're looking for a length that's exactly as long as we asked for. We used two methods to identify these sources of defects. We used simulations and experiments. So these simulations were done in OpenFOAM, which is a computational fluid dynamics solver. So we extruded, imposed a pressure of ink onto a static nozzle, and then had a moving bath moving past it, and so that would extrude a single filament. We also used in situ imaging experiments. So again, we have a static nozzle and a moving bath, but this time we have a camera looking at the tip of the nozzle so that we can see what's happening as we're printing. And then once the print is over, we can remove the nozzle and go back and take images of our print. So for these experiments, we printed straight lines where we looked at the lines head on to identify their cross-sectional shape and printed them out from the side to look at their lengths. So first, let's talk about how rheology influences filament defects. In this section, we're going to have no surface tension, and our ink speeds will be set equal to the stage speeds. So I'm going to investigate a variety of different rheological behaviors. So one type of material that has been printed is the Newtonian material. So usually in these papers where they're using Newtonian materials, they'll have some sort of stabilizer at the interface. So they'll be printing oil into water, but they'll have a particle that stabilizes the interface so that the material doesn't break up into droplets. In our simulation, we use Newtonian fluids in order to identify what is the effect of viscous dissipation on this process. We don't want to have to worry about yielding or elasticity or anything else, just viscous dissipation. We also simulated Herschel-Bulkley fluids. So these are the fluids that are like the fluids that I talked about in the beginning, where they're going to behave like a solid up until a yield stress, at which point they're going to behave like a shear thinning liquid. So for these simulated fluids, all of the behavior in the shear thinning region is going to be the same. These are all going to have the same viscosity above yield. But below yield, they have different viscosities, which I call the plateau viscosity. So that is going to extract just the effect of what the unyielded properties of the materials do to the structure of the filament. And then finally, for our experimental fluids, we're going to look at a variety of fluids, but generally they follow the same pattern, where they're shear thinning, but as you increase the amount of rheological modifier in that material, you're going to shift this entire shear thinning curve upwards, so increase its viscosity. So what I'm showing you here is laponite and water. So laponite is a fumed silicate, and it'll form these structures that will give it a yield stress and give it shear thinning properties. So first, let's look at our Newtonian simulated materials. Here we're going to be looking at cross sections, and ideally these cross sections are going to be circular. If they are too tall and narrow, then you might end up with anisotropy in your final part, because you'll end up with a different resolution in your XY direction than your Z direction. We're also going to be looking at a circular shape because if there's any sort of sharp edges on these filaments, That could lead to porosity in the final part, or it could lead to surface roughness, both of which would be problematic. So for these Newtonian fluids, remember this viscosity is going to be constant with strain rate. And so here, what you can see is if you look down these diagonals, you can see that the cross-sectional shape is the same. So what that tells us is that the viscosity ratio is what's really controlling the filament shape here. So that's the ink viscosity divided by the support viscosity. Now let's look at Herschel-Bulkley fluids. So here we're going to have a constant plateau viscosity up until yield stress, at which point the viscosity will drop off towards shear thinning behavior. So here what you can see is if you go to a high plateau viscosity for both the ink and the support, beyond a certain point, all of the cross sections are the same. So all of these Herschel-Bulkley inks behave similarly and all the Herschel-Bulkley supports behave similarly. And remember, the way that we set these viscosity curves, the viscosity above yield is the same for all of these. So we can identify why that happens by looking at slices of our simulation. So here I've sliced through the bath and the color is indicating the viscosity of the fluid. So in the center of these plots, you can see there's this sort of white outline. That's the outline of the filament. So inside the filament, the viscosity is about 1 to 10 Pascal seconds for all of these. And then there's a yielded zone outside of the filament where the support is at about 1 to 10 Pascal seconds. And then outside of that yielded zone, all of these supports are at a different viscosity, which is their plateau viscosity. So because we have the same viscosities within the yielded zone locally, that means we have the same local viscosity ratio for all of these plots, and that's why we get the same filament shape. So we learned here that the local viscosity ratio is what controls the filament shape. So now let's look at our experimental fluids. So here, our local viscosities are going to change, and they're going to increase as we increase the concentration of lapinite in the material. So here we're printing lapinated water into lapinated water, but our ink has a little bit of dye, so we can see contrast. So if you look at the bottom right corner of this plot, you can see that as we go to high ink viscosities and low support viscosities, we get circular filaments. If we go towards the top left corner of this plot, where we have low ink viscosities and high support viscosities, we get very tall and narrow filaments. And these filaments also get sort of sharp edges at the top and at the bottom of the sides. So in order to compare this to the simulations, remember the simulations taught us that the local viscosity ratio controls the filament shape. So let's identify the local viscosity ratio. You can get that by taking your print speeds, so the speed of ink moving through the nozzle and the speed of the stage moving underneath the nozzle. Divide that by the dimensions of the nozzle, and that'll give you your shear rate. Plug that in, you can get your local viscosity. So in the top left corner, you can see those dotted lines. Those are our local shear rates. So that's how we get our local viscosity. So here, what you can see is that as you increase your viscosity ratio, you decrease the cross-section height of a wick. That occurs in both our simulations and our experiments. And there's pretty good agreement as we go to higher viscosity ratios. So what this tells us is that if the support is more viscous than the ink, it just ends up squeezing the filament vertically and creating these very tall and narrow aspect ratios. Another thing that we can note here is that you need to go to a viscosity ratio of greater than 1 in order to get a circular cross-section. So the ink needs to be a little bit more viscous than the support to get to this ideal circle. Okay, next let's look at how surface tension influences filament defects. So we're going to introduce some oil-based inks that we're going to print into our water-based support. So here we're simulating some filaments that are being extruded into a bath at a surface tension of 40 millijoules per meter squared, which is about what you would expect for oil and water. So you can see again, as you look down the diagonals at high viscosities, the viscosity ratio is what is controlling the filament shape here. But as you start to go towards lower support viscosities, we see a little bit of deviation and we see filaments breaking up into droplets or just clinging to the nozzle as a singular droplet. If we compare that to our experiments, Here, these experiments are covering a smaller region of this viscosity map in terms of the local viscosities, but you can see we get the same pattern, where at low support viscosities, we get filaments that break up into droplets or start to go towards a spherical shape. And if the ink viscosity is low, you get filaments that break up into droplets. If the ink viscosity is high, you get a full filament that then shrinks back towards a spherical shape. If we go to high support viscosities, we suppress that breakup and we still get continuous filaments. However, they are pinched. So if you look at the cross-section of these filaments, they're a little bit taller and narrower than the circular cross-section that we're looking for. So that pinching is the same sort of pinching that we saw with our water-based inks, where we have tall and narrow filaments that occur at high support viscosities. So in order to map these oil-based inks onto some sort of constitutive relationship that tells us how we can balance all of our properties, we can use the capillary number. So that's the speed of the ink times the viscosity of the support divided by the surface tension. So that capillary number is telling us how we need to balance the viscous dissipation in this system against surface tension. So here you can see that as we increase the capillary number, we get a taller cross-section height over width. And so that's telling us that we get more pinching as we go to those higher capillary numbers. So that's less than ideal. However, these aspect ratios are not as tall and narrow as the water-based inks that we saw. And I'll also note that when you have these oil-based inks, you don't get any of the sharp edges or flat bottoms that you see in these water-based inks. So we always have rounder filaments, which is going to be an improvement for our surface roughness. If we plot the length of these filaments as a function of capillary number, you can see that we get longer filaments closer to the ideal length as we increase the capillary number. And so in order to suppress that shrinkage that I talked about at low ink viscosities and low support viscosities, we need to use a high capillary number system. So as a trade-off, we'll have to be able to deal with a little bit more pinching and a little bit taller aspect ratios than ideal. Another advantage of using an oil-based ink in a water-based support, or vice versa, is that you can suppress swelling. So these inks are made out of polyethylene glycol diacrylate with water and dye, as well as some fumed silica as our rheological modifier. And you can see here that these filaments are much, much larger than they are intended to be. And the reason why that happens is because these inks are about 60% water, and the support is about 97% water. So you get an osmotic pressure that drives water from the support into the ink and causes the filament to swell. And that's going to cause a lot of problems because as you're printing your part, the filaments that you've already printed are going to be swelling, and you're going to be printing new filament that is smaller. And so you get a lot of geometric inaccuracies, and you could end up with problems with fusion. So suppressing that swelling is really important. So to summarize, embedded 3D printing, or embedded direct ink writing, is a really useful tool for printing low viscosity materials, and really has a lot of promise in the bioprinting space because bioprinted materials or biomaterials tend to be low viscosity and have specific properties that you're looking for when you're printing cells and things like that. If you're choosing a support for embedded 3D printing, you need to make sure your local support viscosity is slightly lower than your local ink viscosity near the filament. And finally, a non-zero surface tension can be useful if you want to produce rounder filaments and suppress surface roughness and swelling, but you need to choose a capillary number that is high enough to suppress shrinkage. So you can use your support viscosity and you can use your surface tension to make sure that you don't get filaments rupturing or shrinking back towards a spherical shape. So with that, I'd like to thank you all for listening, and I'd be happy to take any questions.
All right, thank you so much. We have tons of questions, which is great. As a reminder, if you are wanting to submit a question, please use the Q&A tab which is to the right of the chat and participants tab. All right, so the top question right now is, could you please share the presentation with us? So,
yeah, if you want to see the presentation again, you can email me, leanne.friedrich@nist.gov, which should be in my profile.
it's always a good question. That means there's lots of interest. That one got voted up a lot. Also, just so you know, these presentations are recorded and there will be information on how to access that. All right, next question is, when will we be able to print brains?
Yeah, I think we're a long way off from brains. Things like ears, things that are mostly cartilage, we are pretty close to printing because they're so simple. Things like livers and kidneys and hearts, those have very complex vasculatures. You have to get all of these really tiny capillaries in there. And so it's going to take, and there's a lot of material variation. So it's going to take a lot longer to get there. So brains, I would say decades off.
All right. What are your thoughts on the applications of different 3D printing processes like FDM, SLA, binder jetting, DED on bioprinting? How could each of those be utilized?
Yeah, there's definitely a range of opportunities for that. Even things like metal powder bed processes are useful for bioprinting if you want to do like a bone scaffold. Yeah, FDM, I would see probably fewer applications for internal use. Things like prosthetics you can already do though, which we saw earlier today. And that goes for SLA as well. Yeah, I mean, for both of those, it's the material space limitation. So a lot of the biomaterials, they're not going to be thermoplastics. They might not necessarily be photopolymers because a lot of them have toxicity problems. But I wouldn't say that this is the only viable method for bioprinting. It's just very useful for soft materials.
Awesome. What limits the maximum print support matrix or something else?
Yeah, for maximum print speed, you're going to end up with the same limitation that you have with conventional direct ink writing, which is that there's going to be some maximum pressure that you can get to extrude your material out of the nozzle. Because you can use lower viscosity materials here, you can probably get to a little bit higher speeds than conventional direct ink writing because your viscosities just aren't as high. But if you want to do bioprinting with very high resolution, then you're going to get to a smaller nozzle, so that limits your pressure. So a lot of the limitation comes down to extrusion pressures. There are also problems when you choose certain print speeds. If you choose a certain ratio of support speed to ink speed, then you might end up with your filaments breaking up into droplets. So that has to be finely tuned. But this I think you can get up to pretty high speeds theoretically. We just haven't looked at the maximum yet.
All right. This one's kind of similar. Are the different printing speeds predefined by the manufacturer of the bioprinter?
Yeah, I mean, the printer that I have, it's a CNC mill, which we removed the CNC from and then added a pressure extruder. So that's me defined.
All right. One last one. Can the vibrations from the 3D printer's head movements shift the material around while printing, or is the viscosity high enough for everything to stay in place?
Yeah, I think that's definitely a good question, because there's a potential that you could, if you're coming around a corner at a very high speed, that could induce a vibration that would be high enough shear rate to actually disturb the entire bath, and then you'll lose that solid-like behavior. So that is something that you have to take into account when you're choosing your print speeds and choosing your path design. Making sure you don't have those fast turns, which cause a lot of problems in conventional direct ink writing and also cause problems here.
Awesome. Well, thank you so much for such an interesting talk. I had no idea that there was so much physics in this technology, but I was just really, really excited to see that. So thank you again. And we will set up our next speaker. So let's see here. All right, our next speaker is DC Fernandez. DC is the Presidential Diversity Postdoctorate Fellow in Chemical Engineering at Brown University. She started her undergraduate studies in Brazil at the University of Sao Paulo and finished her BS in Chemical Engineering at UIC. She received her PhD in Chemical Engineering at the University of Illinois at Chicago in June 2015. She loves working with nanomaterials for 3D printing, nanotechnology, and biosensing. She has a long list of awards that I won't go through, but great job on those. She's passionate about outreach, working with underrepresented groups. She has a lot of accolades, and we're just so glad to have you here, DC, and take it away.
Thank you. Can you see my screen?
Yes, ma'am.
Great. Okay. So she's currently a presidential postdoc at Brown, but I'll be talking a little bit about the work that I did during my PhD at the University of Illinois Chicago, and also part of the work was done at University of Bordeaux at a Centre Research Pascal in France. About graphene moisture gel for aligned 3D printing for electronic and mechanical study. So trying to understand a little bit the background and why we did this research is the idea came as if a light bulb breaks at home. Could be that if you could just go on your computer, 3D design a light bulb and 3D print at your house, and the same idea would be for solar panels or other electronic devices. More, we saw on 3D printing full houses, right? So this house was 3D printed just under 120 hours in Europe, but now we have a huge complex in Texas that was fully 3D printed. There's just so many different applications for 3D printing. Why don't we try to create something where we would have the blocks made out of graphene and some other conductive material, energy storage with the same way, having the cables and everything already 3D printed. So that's really the goal in the future where we want to get, where we could implement those of the house also on the 3D printing process, where the whole house would be fully 3D printed. So which materials did we use and how we use it, and what it's going to be on this is I want to talk a little bit about the materials, the process, and how we use the 3D printing. And the 3 studies that was done was the mechanical, Raman is about the and the electrical analysis of the structures. So the material that I used was, the first one that we started with was graphene. We were buying this filament. So graphene was, for whoever is not familiar, discovered in 2004. As you can see on the image, was just a honeycomb, and is nothing less than, if you separate the layers of graphite and you come to just one thin layer of the graphite, that is actually what graphene is. So what is really interesting is because graphene is so thin that the conduction happens in just 2 directions, so just X and Y. That's why it's called 2D nanomaterials, because we don't have that 3rd dimension, and that brings a lot and fight. So even though once we stack the graphene together, what we want to try to create is have this 3D printed structure with graphene, but the properties of graphite. So having now these amazing properties, that is a super capacitor, can be used for LED lighting, it can be used as a sensor. There's just so many applications that graphene can be used for. But a lot of that is lost to go to. That's what we're trying to get. We're trying to get these 3D properties of graphene with a larger devices. Started with Bosch filament. We were able to 3D print the structures that was conductive and would had some properties. But when we're buying the filament, there's a lot of not just PLA but other materials. Of course, the company did not. And so the idea was to try to find a way to make the materials ourselves. And once we try to figure that out, we also try to think, okay, which other can we use besides of graphene? So we add 2 other materials to the research. One material was mobilium disulfide. MOS2 brings the semiconductor property. So graphene is always conductive. It needs a little more the on and off switch of electronic applications. So if we're thinking about not just electronic components of the house, but if you think of electronic device, your cell phone, you always want to turn on and off. So MOS2 would bring that. And bottom nitride would bring the insulation capacity. So bottom nitride, if you think about a cable or something for your device, or in the case of the electrons should be confined inside of that cable. So the bottom nitride would bring that property to it. So how do we actually do that is time, tissue scribe 3D printers and all of that. We didn't have any of that. We didn't have money for that either. And part of Grow was they could pay for me to go to France, a professor there. He modified the 3D printer to 3D print with a syringe. So we made the gel, we mixed the graphene and MOS2, and we 3D printed that, and after we doing lyophilization. So the first part of the process was mixing graphene and MOS2. We use a TIPE sonicator that's done a lot already with many different materials. But the interesting thing is that what a lot of people do, especially for graphene gel, is supercentrifugation. Once we use graphene and MOS2 with the difference of density, we have the phase, and that meant that the supercentrifugation anymore. So we had to find a different way to concentrate the solution and create the gel. So when we're starting, we have this graphene solution for 8%. Extremely low concentration, so we have to increase that a lot. And the idea that was done for some carbon nanotubes was like over here. So on here, as you can see, this on this vial over here, we have dextran solution around it. Dextran will remove the side of the membrane, concentrating our gel and creating the gelation of our material. The problem is that I had just 3 months in France. I didn't have spend 1 week to just obtain one gel. So the first novelty of our process was using this absorbent gel, where we cut the time to about 4 days for some of the materials, and some of the materials I was able to 2 days, as you can see here in the bottom. So this was the first novelty, and from the first day we could already see the liquid crystal phase of graphene. So this is the same material day one, and really showed that the material was maintained properly from day one, and we were able to make a different concentration. So this is starting from just graphene and to 90% to 10% of graphene. So how the MOS2 was used in powder. So this was great. And even though the MOS2 was bulk, we still were able to mix it well and obtain the gels. Obtain this different concentrations of gel, we have to understand a little bit of the rheology. So Leanne just went over a lot about, so I won't go into much details because she did a great and a lot about. So what we did here on this, and what I want you to get from here is really just how the material behave and how we proved that this was actually a gel from using the grass. So there were 2 points. So in our materials, our gain modulus was always above the loss modulus. What it means that for all our materials, we actually obtain gel. And what was really interesting too from our material was viscoelastic. Graph of the flow sweep, the material went back to its original property almost every single time. It went almost to the same point it was before. It was really close to all of that. It's cool to see that viscoelastic. So After that, we had the rheology done for all the different concentrations of graphene and MOS2. And why do I really think about the rheology of that is because there were two different ways to figure out the alignment of the printing. So we could look at the crossover point between the G prime and G2 prime, or the Hershey-Buck. So doing those two methods, we had to ensure that the pressure that we were printing was above of the shear yield stress. The videos, if it shows, I'm not sure if it's showing. Okay, so as you can see here on the video, there is a black part on the 3D printer, and the black part over here is just a what measures the pressure as you're printing it. And this pressure was really important to prove that we're actually having the alignment. So in chemical engineering, when we learn about flow and plug flow, sure that this shear yield is. So we did that for all our samples, and we were able to 3D print all the different samples. So this one that is showing here, the hollow cylinder printed, was the mechanical stress. That was the first study that I did while I was still in France. So here, what is happening is we're just pressuring it and measuring the tensile stress, and with that we vary the different concentrations of MOS2. And what was really interesting, as you can see, as we increase the amount of MOS2, we also increase, meaning that the material becomes brittle. So we did all the mechanical stress, and that makes a lot of sense because of MOS2 and all the water. So we did lyophilization, we dry the sample. So the sample has a lot of water in it. To remove it, you have all the porosity that becomes easy to kind of crush it as we're doing the mechanical stress, and the material do not return it at all because of all the porosity. The different ways. After that, I brought it back and I did the Raman study. So what is Raman, for people who are not familiar with it, is a laser that uses phonons. So the phonon shines through the sample, and when it shines here on the bottom of the sample, the material will vibrate either in plane or out of plane. And once the phonon returns back, this detector will give a specific peaks, that those are kind of the fingerprint of for graphene. And in our case, I had MOS2 and graphene oxide because I did lyophilization, the freeze. I also put in the oven for oxidizing. So I had reduced graphene oxide. And after the reduction, we don't have that third peak that you showed before. So as you can see here, MOS2, those are the peaks of MOS2. And in this case, show the peaks of MOS2 and graphene oxide. So why was this study important? Why did we talk about the vibration? Once we want to learn about the electrical characteristics of it, we need to understand how big those graphene sheets are. And using that data, we can obtain the average size of the graphitic region domain. So those is about 8.3 average that we got from our samples. And another thing that was even more important in this case, looking for all different samples. And as you can see here, we don't see the MOS2 in this case because we have of MOS2. As we increase the amount of MOS2, you see the peaks throughout the whole device. And those scans is done 20 microns apart. So every line you see is from the top of the sample going 20 micron in depth as we're scanning those samples. So as you can see, all of this show all the characteristics for all the material that we have. We can obtain concentration. Value means how many free electrons do we have flow to be able to flow on this device. And this was really important for the electronic applications of our devices that we wanted. So we go a little bit farther and we use a cryostat, and we have the electrodes connecting in the two ends of an electronic device. And once we connect those two ends of it, and we the current voltage from going from 17 Kelvin to 200 Kelvin. Sorry, I should have a unit here of the temperature. So this is varying temperature, and we have actually using the heat, we can energy thermal barrier. So this AA over here is how much energy we need for the electrons to start flowing. So this value is a little bit higher as if we have just graphene. In this case, 16.24. For the graphene is about 8. So that means that we need a little bit more energy for the electrons to start flowing. That really conductivity properties that I mentioned before, the on and off switch that you would need for the electronic application. And the other thing that we can do with the same type of electronic study is doing the following, and that is A over here. This A naught is the average tunneling distance, is how much distance you have between one graphene and the other. And to try to understand this 0.45 nanometer, it's really important to try to determine if the electrons are hopping or tunneling through. And the data that we get here is really what is really important for us in this case. So as you see here, we have a graphene sheet here, and we have another graphene sheet. So the 0.45 that I mentioned is nothing more but the MOS2 distance that we have in between one graphene sheet and the other. So the electron is coming here, and it needs to tunnel through the MOS2. In our case, so the MOS2, it tunnels through the MOS2 and go to the other graphene. So this is really trying to understand the electronic characterization. And the other thing that we had in the study was the 16.24 is this how much energy is needed for the electron to start flowing and tunnel through the material. So as a conclusion, as you can see here on the picture, there were larger printed, have a graphene structure to printed, and there were smaller devices too, as the electrodes and the hollow cylinders. Was really interesting that we were different concentrations, and we were able to, as you mentioned, Leanne mentioned before, when we were 3D printed those gels, especially since we're making ourselves, it needs to be liquid enough to be extruded, to maintain the shape of extruded. So there's a lot to play around and to be able to have those structures and to have it large enough. In this case, even though it's much smaller than the talk that we had earlier today, it's still large compared to some of the materials that are done now with graphene and MOS2. So we were able to understand, characterize the material, understand the electrical study, and I want to all the funding agencies that helped me to conclude this research. This is still ongoing. We want to have a lot more research done with graphene MOS2, graphene and bottom nitride, and maybe mixing all of them. I just purchased the to be able to printed more materials now. Those two are my advisors, Vikas Berry from University of Illinois Chicago, and this is my advisor in France, Philippe Poulin. And I would take any questions now.
Awesome. Thank you so much. That was super interesting. I think we're all looking forward to see what the future holds for this technology. We have a few questions. First one is from Leanne. She says, this is very cool work. Does the conductivity change when you stress the printed structures?
Yes, it does. So I didn't show here even with just the filament, the PLA filament and graphene, it changed a lot. So it really varies. And what was interesting, that what actually really affected the most was the part where it was most tensed. So the part where it was most stretched was really what was driving the conductivity of it, the filaments to their printed structures.
Awesome. What are the next steps for tailoring the fluids for more accurate or high resolution deposition?
So the first thing is trying to control better the ammonium nitride that has been in the TIPE sonicator. The MOS2 and the bottom nitride, when I first did in France, I did not do the characterization there. I did it here, and all of the materials were still bulk, and that influences a lot of the characteristics and the property afterwards. So I'm trying to get them to be well mixed and a few layers and not have them in bulk, because that will really affect the properties. So that's probably the first step. And the second step would be to get better printers for the deposition part, and hopefully have more money for research to get a better printer.
Awesome. All right. Are there other carrier fluids you've considered that dry more quickly?
Not yet. There's a lot of other materials that I want to work with. Maxines that are coming out. There's a lot of other materials that are still potential for research, but I haven't done it yet.
All right. How might carbon nanotubes affect the properties versus graphene, or would it affect the viscosity, or would the effect on viscosity be too significant?
So it really depends on the application that you would want. The applications could vary a lot, especially, for example, one of the applications that we want to get after is actually having materials intercalated. So if you think about it, like virucidal or some other materials that you want to try to create that and still have that surface slowly releasing some material, the carbon nanotubes wouldn't be able to hold as much as graphene, as this graphene would be just in between. And so it really depends on the application that you're trying to use. For the electronic applications would be the same thing. It varies on how you want to use that afterwards and how the properties that you want to obtain.
Great. All right, last one. When will you be able to print a simple blinky with an LED circuit? I guess a blinking LED circuit is what they're asking.
Yeah. I'm not sure. Hopefully soon. We're behind on that. My first goal is to have the energy storage. With the graphene MOS2. MOS2 is really you can emit light with it, but it's not able to see. You will see it with the detector, but not with naked eye yet. So hopefully, if we can create something that we can really detect it, that light emission from MOS2, we can actually get to that point soon. So we'll see. I'm working on it now. Hopefully we can get that soon.
Awesome. Well, thank you so much for this very interesting talk. We will take a quick break before our next panel, which is the latest in light-based AM. So we'll see you back here in a few minutes. Thanks again.
Thank you.